Okay, so let's go ahead and take a look at example 6 here. Find the equation of the tangent line to the graph of f, which is a function f of x equals 3e to the x minus 5x squared at x equals 2. So to do that, the equation of a tangent line, we can go ahead and use the standard format y equals f of a, the y value, plus the slope of the tangent line f prime of a times x minus a. So for us, since we want the tangent line to f at x equals 2, this tells us our a value is 2. So we can already fill in what f of 2 is. We can just plug in 2 into f. So let's go ahead and do this. Let's make these all 2's. F of 2 is 3e squared minus 20. So that whole thing is just f of 2. Plus, we need the derivative. So let's take the derivative. The derivative of f prime of x, is 3, and the derivative of e to the x is itself, so e to the x again, minus 2 comes down, multiplies with negative 5 to get negative 10. Power rule, subtract 1 from the exponent. So f prime of 2 here is actually 3e squared minus 20, which is, this is coincidentally equal to, or let's just say, same as f of 2. That didn't have to work out that way. So in this case, we're going to have that whole expression again, 3e squared minus 20 times x minus 2. And that's the equation of the tangent line. All right, example 7 is talking about this above theorem here. If a function is differentiable at a certain location, then that function must be continuous there. But is it true in the opposite order? So if a function is continuous, must it be differentiable? The answer is no. Counterexample here would be the absolute value of x. This function, the absolute value of x, is actually a piecewise function. It spits out x if the number you gave was already non-negative. It spits out negative the number, so opposite the number, if that number were negative. So for example, the absolute value of negative 2 is negative 2, which is 2. So this function is actually not differentiable. There's a couple ways that we can see that it's not differentiable. The one way is graphically. If we graph it, this creates a V shape. And it's really important that this is a right here at x equals 0, where the two pieces, the actual V meets right here, this doesn't kind of smooth out. It's not like a really quick turn. This is a corner. This is a 90-degree angle. This right here is a corner. It's a location of not, you can't differentiate there. So it's not differentiable at that location. So we can also show this by actually attempting to take the derivative. Okay, so if you try to take the derivative of a piecewise, we could just take a look at the derivatives of each piece. right? If somebody walks up to you in the street and asks you, what's the derivative of a piecewise function? Naively, you might suggest, well, I guess we could just take the derivative of each piece and create a new function. You totally could. Let's see what that is, though. The derivative of the top piece is just 1. The derivative of the bottom piece is -1. So do you see how the one piece's slope doesn't agree with the other piece's slope? Because these two numbers aren't the same, the left-hand slope, -1, does not equal the right-hand slope, +1. Because the left and the right-hand slopes do not agree, the derivative does not exist. That sounds a lot like a limit. And that's exactly why. Because what is a derivative? It is a limit of slopes. So if the slope on the left doesn't equal the slope on the right, that's really saying that the limit on the left doesn't equal the limit on the right. So it's not true. Last thing we want to say here, not enough for its own video, but local linearity. So a function, if it's differentiable, it means that you could zoom in on that location and it would eventually look like a line. So for instance here, if we have a curve like that, and I have a tangent line right here, you can hopefully convince yourself that if you are close enough to this point, the actual black curve and this red tangent line become one and the same. They overlap. Even from far away, there's a little bit of distance away from this red point where it kind of is hard for us to tell that the red and the black are different. So if you were to zoom in using like a graphing calculator, maybe like, a 10 times magnification on this little area here, you would only see the tangent line. So the issue here with absolute value is if we zoom in 10 times here, this doesn't ever, at that where the two pieces meet, this never flattens out and becomes a line. It never looks like this line, and it never looks like that line, and it doesn't look like any other line. It always has this V shape, always. It never flattens out, and that's the issue.